And am I on the screen? Very good. Okay, so what's our big picture? We know how fast the quantity's value is changing at every moment. What's that? You know how fast the quantity's value is changing at every moment. At every moment it's constant rate of change. The same constant rate of change at every moment? So how do we know the rate of change at every moment? Function, rate of change function. It changes where different values of the infinite variable, right? That's the red curve. Function gives us different values for different values of input, right? So it's a rate of change function. We know how fast the quantity value is changing every moment. We want to know how much of the quantity you have at every moment, right? That's this accumulation function that we're building out of it. So what do? The first thing we do is take that rate of change function and do what to it? Make it awful, right? Why do we make it awful? Exactly. We make it worse than this beautiful exact rate of change function that we have. Why do we mess it up like that? We need constant rates of change, right? We can't do it if we have a continually changing rate of change. We need constant rates of change to have any chance to start building accumulation, meaning little changes in the quantity, right? So constant rate of change, we know the math of that, right? What's the math of constant rate of change? Two important principles, constant rate of change. So it's on the video. Okay, so what are we turn this changing rate into constant rates of change because constant rates of change can help us build accumulation. How do they allow us to build accumulation? How do we get accumulation from rate of change? What are the things we're adding up? That's the key. What are we adding up? In what? Y. And how do we get changes in Y? MDX. Right? Given a constant rate, M, this formula allows us to compute a little bit of change. And then what are we going to do with that change? Right. Our accumulation function is going to have the general format of Y initial, all the accumulation from before, plus a little more change. And if we keep doing that over and over again, we're building an accumulation function, right? We keep keeping track of everything we've accumulated before, and we add a little bit more change. And that builds an accumulation function. Yes, sir? Or not? Sorry.
This has to do with like the juicy calories.
Yeah.
Are we able to like do function notation and like in like a second graph? So like if I want to do a of x, but like on the second graph, so would I like do like a prime of x or a prime x prime? Like is that possible, or would I just put y prime?
It's not about the x prime or the y prime. All the x prime and the y prime are you've got a function and you want to graph it.
Okay.
But the idea that you're talking about is yes, right? So the y initial, where's the y initial come from?
Previous.
All the accumulation from before.
Yeah.
And where are you going to get that?
From the
Previous segment.
Yeah.
Exactly. Right. Exactly. Okay. So That's the general gist. So here's the example we worked on last time. We wanted to, so we're starting A here a little bit after 2. That's our starting point of the accumulation, and we were letting x increase through intervals, delta x intervals, accumulating along the way, right? And so we wanted to say, okay, what if we had this, if we were building this accumulation function, what would we have at a of 6.75, right? What would a of 6.75 be? And we said it would be the dy summed up from what? There were 2 parts to it, right? There were 2 parts to it. So if we wanted to get the accumulation up at 6.75, we would accumulate the dy's where? What's that? What do we call those? All the previous intervals. Completed intervals. We want the change from the completed intervals. So dy plus dy plus dy. And how are we calculating each of those dy's? mdx, 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 right? The rate, constant rate times change in x, constant rate times change in x. So dy plus dy plus dy. And then, to actually get up to 6.75, we have a little bit more change, another mdx from the current interval. Okay, so then we figured out last time that the x coordinate in the jth completed interval, do you remember doing this? What was it, do you remember? How do we get to the x coordinate of the jth interval? Remember what that was? Right, a plus j minus 1 delta x's, right? So there's that. So to get to the left side of any completed interval, you're going to go a plus j minus 1 delta x intervals, where j is just the interval number, right? And then how many intervals do we have to go across to get to the left side of the current interval? All of the completed intervals, right? The total number of completed intervals. So how many completed intervals to reach the current interval? We said all of them, right? And so that would be a, so to get to that left side of that current interval, we're going to go a plus the total number of completed intervals times delta x. And we said this is the function left x. And to find the function of left x, we needed to figure out this formula for the total number of completed intervals, right? So left x is this function. It's this strange function that takes an x but gives you back another x. It gives you back the x value at the beginning of the current interval. Right? So what is left x in this situation right here? So what is left of 6.75? What's left of 6.75? Practice with left here. What do you say left of 6.75 is? Three. Is it 3? 3 delta x. So just estimate its value. Just give me an estimate for its value. It's about what? Okay, 1.1. Agree with that? Okay, what is left x? What is left x? Glad I asked the question. No, I'm not asking you to compute that equation. I'm asking based on the principle of left x, just give me an approximation. I'm not asking you to compute anything. Okay, she says 1.1. What do you guys think? Other possibilities? Or do you agree with 1.1? What about 6? So we got 1.1 and I got 6. Any other nominations? You want to change your mind?
Yeah,
She wants to change her mind. It's more like 6. Tino, what do you think? Around 6. So I'll say it one more time. Left x gives you the x coordinate of the left side of the current interval, or the starting value of the current interval, the x coordinate. It doesn't give a y coordinate, unless you graph left x and put left x on the y-axis, but we never do that, okay? The left x gives us back another x coordinate, the x coordinate of the start of the current interval. So how, what do you think? Do you think left x is 6 or 1.1? 6.
So we have left x, do we have right x?
No, don't need right x because we care about the rates at the left side of each interval.
Yeah,
that whole interval.
I mean, like, does it
You could-
on GC?
What?
Does it raise?
It doesn't know. It doesn't know. GC has no clue about a function named left. You could define a function named left, but it has no clue. It doesn't know. It doesn't know functions by the names that you give them. So if you want to define left x in GC, that's great. It'll do exactly what you tell it to do, but it has no clue about this thing that we're talking about, the left side of the current interval. Does that make sense? You have to define it so that it does that. Yeah.
So since the x is at like, what, 6.7,
Right.
left x is 6.
Right. Okay, so now what's left of 4 about? What's left, if I said left of 4, what would you estimate left of 4 is? About 3.3. Do you see that? It's about 3.3.
Is it x like where these dots like the intervals?
It's the beginning of the current interval, right? So the red dots are showing you the delta x intervals, right? The delta x intervals. So left x is the x value at the beginning of the current interval. So do you see that left of 4 is about 3.3? And then what's left of 8.1? What's left of 8.1?
Oh, that's about 7.3.
What do you think? About 7.2? Something like that? All right. What's left of what's left of 7.5? Is it equal to left of 8.1?
Yeah.
Exactly equal to? Exactly equal to, right? Whatever we guess for left of 8.1, it's going to be the same result for left of 7.5. And why is that important? Because we need that rate of change. So now, what is the rate in this picture? What is the rate of change of left x? So what is this then? So this composite function. So we put in 6.75. We get left of 6.75, and then we take that result and we get the rate. So what is that approximately equal to? 1.1. Agree?
Oh, okay, gotcha.
So what does that tell us? It tells us that at 6.75, what's the approximate rate of change? 1.1, right? For this whole interval, the approximate rate will be r of left of x, or r of about 6. And you get that same rate then for all x values in that interval. You see that? So every x value in that interval, left x takes you back to that. And then r of left x gives you that rate, and so then it's constant rate through the whole current interval. So review. How much do we have at any current value of x? So that was all about 6.75. So now at any current value of x, right? We have the accumulation due to the completed intervals, right? Plus. So can you remember what that was? How we wrote that at the end of class last time? Summation of, no, so this is now any x, right?
Oh, okay.
So it's going to be what? So they're all rate times delta x, right? So rate at what? A plus j minus 1 delta x, right? And that rate times delta x. And then to get every completed interval, what do we need? Where are we going to start with? J equals 1. And we're going to go up to what? What are we going to go up to? So what's the last j for our completed intervals? J changes, right? So j is going to be 1, then it's going to be 2, then it's going to be 3, then it's going to be 4. When is it going to stop? What value will it stop at? Now we're talking about any x. Any x has gone through any number of intervals. So for the completed intervals, where's j going to stop?
Is it to be a number or just?
Yeah, because these are whole numbers, right? This is j is the interval number, completed interval number. Right? So j is going to start at 1. That's talking about interval number 1, the first completed interval. We're going to get the dy, right? Then j is going to be 2. And we're going to be talking about the second interval, and we're going to calculate the dy, right? And dx. Then j is going to be 3. So when is it going to stop? Okay, but j is only talking about completed intervals, right? So don't worry about the current interval. So if j is the index on the completed intervals, then when's it gonna stop? But these j aren't x values, right? J aren't x values. J is the interval number, first interval, second interval, third interval. So those are different than x. But it's just going to be the last one's going to be the number of completed intervals again, right? It's all the completed intervals, right? For whatever x we have, j is going to go from 1 up to the number of completed intervals. Okay, so I have a much prettier version of that.
We can't do this on GC.
Oh, yes, we can.
On this assignment?
No, on this one you're turning in today. No, don't do it on this one.
Oh, okay.
We're still, this is the last, that assignment is for writing accumulation as a piecewise function or separate functions. This is coming up. Okay, so the accumulation due to the completed intervals plus the accumulation so far in the current interval. How do we define that? What's the accumulation so far in the current interval? How do we get that? What's that?
R of left x times delta x.
R of left x times delta x times dx times dx. Okay, and so what is dx? So we want to write everything in terms of x, right? So dx is how far we've gone in the current interval. So how can I write that in terms of x? What is dx? Just think about what you've been doing whenever you use dx in these equations, right? In these accumulation equations. So what is dx?
Dx is like how far it is within the interval of the delta x.
So it's
So is
or
it
the x final.
Okay, so what is x final and what's x initial?
x final delta x?
The x final.
Look at the picture. Look at the picture at the bottom.
It's
What's
so it's a bunch of numbers.
No, we need a function of x, right? Right now we just have dx. We don't want that. We want this to be a function of x. This is just like what we've been doing the last month. Whenever you had this, plus m dx. How did we write dx? X minus x naught. But what's x naught? What's the x value at the beginning of the current interval? We just talked about that. Left x is the x value at the beginning of the current interval. So dx will be x minus left x. That's not the next thing I want to talk about though. Okay, so we'll put that in. So x minus left x. So the only thing left is how many completed intervals at value x. That's what we did at the end of class last time. Remember? So remember, j is going to go from start at 1, and it's going to go to the total number of completed intervals. What is that? How did we get that from whatever it was?
I just know it in terms of numbers.
So you gotta distinguish between x values. Here's x values: 1, 2, 3, 4, 5, 6, and counting intervals. Those are two totally different things, right? First interval, second interval, third interval, fourth interval. That's what j does.
Oh.
While x is coming along here going 1, 2, 3, 4, 5, right? So x and the number of intervals, they're on the same scale, kind of, but they're different.
What's the floor of x minus a divided
Right. Remember, we
by interval?
floor it, right? Floor it. So the number of completed intervals was x minus a divided by delta x, and then take the decimal off. What is dx in terms of x? We said x minus left x. So we got it. We have it in one line now. So this thing that you're doing in the current assignment, where you're writing each function separately, or like a piecewise function kind of, this does it in one line, right? This does it in one line. For any value of x, it counts the number of completed intervals, and will sum up that many dy's for the completed intervals, m dx plus m dx plus m dx, right? For that number of completed intervals, and then add one more m dx, right? One more m dx, but now in the current interval. So it's going to be the rate in the current interval times dx, the actual like partial, that dx right there. Okay, so we got it. So I'll give you a chance to meditate and digest and ask any questions. So if you were to graph this, what kind of function would you get? If you were to graph this function, capital A, what kind of function would you get? Well, it's a accumulation function, but like, so the visual structure of it, visual structure. But like, for instance, an answer might be, it's a parabola. That's what I'm looking for. The visual structure of it, like visually, what will you see when you graph this? What kind of function? She says it's piecewise. Is it a piecewise function? Okay. Any more qualifications of that? Piecewise. What are the pieces, right? So are the pieces, are they linear? So will you just give a piecewise linear function? So what is it based on? It's based on what? It's based on our approximate, right? It's based on these approximate rates, these constant rates. So if it's based on these constant rates like this, these roughly change, will you get a piecewise linear function? Absolutely. That's exactly what you'll get. Okay, other questions?
If we took the limit of this as number of completed intervals approached infinity, would you approach like the true function?
You already asked? So if we let these intervals get really small, took a lot of these, like let delta x get so small that there's really no difference between delta x and dx. Can't even tell the difference. Like, what would, so that piecewise linear function would have smaller and smaller delta x's. And he's saying it would, then we would be like converging on the true accumulation function. What do you think? Like it? Yeah, that's where we're going next.
I feel like this was like a really good way to explain integrals too. Like you had the area under the curve. Like I never really understood it until you drew out the line. Yeah.
Does this have anything to do with area?
Yes. Right?
Have we talked anything about area? Is your mind seeing areas?
Yeah.
So yeah. So we don't. We're trying to avoid that.
Oh, okay.
It's okay because really this rate of change is the rate of some quantity like volume of oil, or what else have we done? The speed of the basketball, right? And then we're calculating, say, the accumulation of volume of oil or the accumulation of height of the basketball. Those quantities don't have anything to do with area. I know you've been told they do, but they really don't have anything to do with area, right? The height of the basketball.
But like I feel like when we take like for example this one that's horizontal that's above the graph, like I can see that that's like an overestimate.
Right, because why is it overestimate? Not directly because of area, but because your rate was too high for that interval. So if you go at a higher rate over the interval, then you're going to get more accumulation than you should have.
Okay.
Think of it that way.
I guess the area is kind of being seen for me in like the accumulation part. Like, I don't know. I know it shouldn't be, but it's like being seen for me.
Yeah. So we want to so we've tried to turn the tables on this a little bit so that area under the curve is just one quantity that you could look at, right? You could apply this to area under the curve, but area under the curve isn't like the bottom line of it. The bottom line is you have some quantities rate and you want the accumulation of that quantity, and so then you build a new rate of change function. This approximate rate of change function, and you build your accumulation out of that approximate rate function.
So does area under the curve work as a result of this?
Yeah, it's kind of like
Yeah.
right, exactly. It's like you could look at this through the lens of area under the curve.
So
We don't want to look at accumulation rate of change as area under the curve.
Yeah. So this is getting like to the core of why.
Right. So yes, we can take area of the curve and apply this to it, and say, oh look, we can talk about that later.
So the area isn't like the integral; it's just like a consequence of.
It's a consequence of the fact that we graph in rectangular coordinates.
Yeah.
And it just happens to work out that dy is the same value as height times width. And that's only because we graph in rectangular coordinates. So it's like kind of like incidentally. Incidentally, this area calculation is the same as this. But it's not the meaning, right? It's not the profound meaning. The profound meaning is rate of change and accumulation of that quantity that we have the rate of. And if it's volume of oil, it has nothing to do with area, right?
Yeah.
You see? Yeah. And if it's the height of the basketball, that has nothing to do with area. Okay, other questions? Good discussion. Any other questions? All right, where does this go next? All right, so I have an exercise here. So here is Here's a new application, okay? Unloading sand onto a scale. So here's the rate of change of weight as a function of time in hundreds of pounds per second. 100 pounds per second, and then we know what the rate is every second. Okay? So we want, and what's our goal? So we have the rate of change of weight. What do we want? What do we want in this journey that we're on? So say again, how much what? Okay, is that what we want? We want to know how much sand we're adding every second. Is that what we want to know? Or
How much do we have at every second?
So we want all the accumulated weight of sand, right? So we want to accumulate weight. So in any given second, we want to know how much weight is accumulated on the scale, right? So you see the difference between the first thing you said? So it's kind of like you wanted a function of dy's.
Yeah.
But we want to accumulate, meaning at any given number of seconds, we want to know the accumulation of all the sand so far, right? So what do we do first?
Decide our intervals.
Okay, good. Decide our intervals. I want intervals of 0.4. I think I've chosen intervals of 0.4. And then what? Yeah, I have intervals of 0.4. And what are we going to do with those intervals? Our goal is a function that gives accumulated weight of sand on the scale, given the rate of change. So he wants to decide on intervals of 0.4. That's good. Or intervals, I say 0.4. And why? Why are we breaking this up into intervals? She wants the constant rate of change in every interval. And where's the constant rate of change for any given interval going to come from?
The y value at every change in the intervals. So at 0 plus 0.4x. 0 plus 0.4x.
So in any given, so let me try it again. So in any given interval, where is the constant rate for that interval going to come from? Right, we're going to use the left side of the interval, right? So then what will it look like? Can you imagine what the graph of the approximate rate function will look like? Right, so we pick off the rate at the beginning of each current interval, the left x, right? So we're going to do the rate at left x for every current interval. So the rate at left x, the rate at left x, the rate at left x, okay? The rate at left x, and that builds our approximate rate function. And then based on our approximate rate function, we've got our, what? We just made this bad boy, right? What does this bad boy do? Okay, so it's summing up, right? Summing up changes. So can you predict what this will look like? Can you sketch it? Can you sketch what A will look like in this situation? Everyone, get a piece of paper and a pencil, and try to predict. What do you think this function is going to look like based on the approximate rate function? I'll be right back. One more of these. Yeah, the weight's going to decrease? No, okay. It's good to think about. Good. Yes. Okay. Oh. What's the rate? Is the weight ever decreasing? This is the rate of change of weight, right? Is the rate ever decreasing? I'm sorry. Yeah, is the weight ever decreasing? This is going up slowly, going up fastest, and then is the weight going up or going down here? The weight. The weight. This is the rate of change of weight, right? Still going up, just slower, right? So the weight is always going up. Okay, here we go. So I'm graphing this thing right here. This is graphing capital A. This is graphing capital A. Right? In your volume of oil function, you're doing the exact same thing, but you're doing it with separate functions, right? And you get the same kind of graph, right? Piecewise linear. Piecewise linear. Abrupt changes in rate. Because we have constant rate and then abrupt change in rate. And then an abrupt change in rate. And so that happens at every corner,